My name is Eray Özkural, and I'm the founder of a startup called Celestial Intellect Cybernetics. So the adapter is not here, and to avoid wasting time, I won't show you the presentation. My paper is about universal completeness and objectivity of induction. So, well, what does that mean? In algorithmic information theory, an open problem is the choice of reference machine. As you know, the reference machine is completely arbitrary. So it can be any universal computer like the Turing machine, or Lisp interpreter, or something else like a neural network, recurrent neural network, right? So which one would be best for AI? And well, there is this theoretical solution to that problem, which is the invariance theorem, which assures us that there is only a constant program size difference when you switch from one reference machine to the other. But is that enough? Well, for most problems, it's not, because most problems are actually not that large, especially if you're using stochastic models. So if you try to implement the C interpreter in Lisp, it would actually be long, and vice versa. So we actually want to avoid that, that additive factor. So how do we do this? That was the beginning of this work. And the other thing is Solomonoff induction really complete in the physical sense, which is to say, will it work well? Is it always guaranteed to work in this universe, which we live in, which we inhabit? So those were the two considerations that led to this study. I actually wrote this, well, I was trying to define some better measures, some better definitions for my new, the next stage of my algorithms. So that's how I started. What Solomonoff said about this problem was this. Well, he said he actually found an objective reference machine, but then he said he didn't have any need for it. Well, why was that? Because, well, obviously, you have to encode background knowledge, and in Solomonoff induction, you encode that knowledge in the reference machine. So, well, say we picked scheme as our reference machine, so you have to encode all sorts of things like who your father was in that machine, so that makes it pretty subjective, as all Bayesian inference is. So Solomonoff concluded, well, I found this machine, which he didn't state, by the way, but we have no need for it, because one of the properties of Solomonoff induction is subjectivity. It's not objectivity. And here I claim, well, there is some objectivity, actually. So how come? So that's what I'm going to try to explain to you without a presentation. So maybe you'll focus better on my words, which is good. So I'm going to try to exploit that. This little adapter doesn't exist, sorry. So there are some equations, but you can find them on my paper anyway. So I was just copying and pasting, so maybe that's not so good. Okay. Well, so completeness of induction and objectivity of induction. Let's get to completeness. What do we mean by it? Well, in the Gödelian sense, completeness meant that you have this procedure that can get you any kind of solution, right? So you can prove any theorem, or in probabilistic terms, you can succeed in any probabilistic inference. Is that possible or not? Or is it optimal? Is it always guaranteed to work? Well, Solomonoff's 1974 IEEE transactions on information theory paper gives a very rigorous solution to that, which is of course, refined by successive researchers, but the main result and what matters is in that paper, as you know. So it's called the convergence theorem. And does everyone know, who knows what the convergence theorem is? That's not impressive. So maybe I should say, okay, well, convergence theorem is the same thing as the proof that in the reinforcement learning setting, IEC always works, right? It's the optimal, whatever, and it corresponds to the same thing, just different setting. So actually, well, do you know the SVM literature, support vector machine literature, statistical learning theory? Is anyone familiar with statistical learning theory? Okay. I'm glad, but I'll have to explain, which is not good. Without the presentation, it's harder. I thought everyone knew it exactly, so I actually didn't have it in my presentation. But I'll upload the file later so you can see, and I'll add that slide too, and some references. So I mean, it'll be self-contained. Okay. Well. In statistical learning theory and also in Solomonoff induction, we have this thing called generalization error, right? So it's an error bound. It quantifies how much error you can have at most. And in Solomonoff induction, for sequence induction, it's defined like this. You have some data. Some initial bit string, and you're predicting the next bit string, right? So that sequence probabilities as usual. And what the convergence theorem states is that you have the data and you keep predicting, right? So until the very end, for all unseen examples, it could be infinite, doesn't matter. And the total error, prediction error of RMS of differences between probability measures is bounded by a constant, and that constant is a small factor. KLN2 is where K is the algorithmic complexity of the stochastic source. So it's mu in Solomonoff's paper. And so we have a stochastic source. It's generating some sequential bits, right? And convergence theorem tells us that under certain conditions, this error, the sum of all errors, is bounded, and which means that you actually need very, very little data for Solomonoff induction to succeed, because assume that we have, say, in the chosen reference machine, 10 bits of algorithmic complexity in the stochastic source. And we also have 10 bits of data. After 10 bits, error per bit decreases dramatically because it's not really growing, right? So Solomonoff says the error is only sublinearly increasing as data size increases. So that's excellent results. It's almost perfect, but not quite, because we have that little complication, which is the K, right? Which is the algorithmic complexity of the stochastic source. And what do we mean by that? Well, of course, it's a non-deterministic computation. So it's the length of the smallest non-deterministic program that perfectly simulates the source's stochastic properties. So that's it's just simulates its probability density function, basically. So when does this work? Well, obviously when you can do that, when the stochastic source has a computable probability density function. So now the question to ask is, okay, well, we have this wonderful theorem called the convergence theorem, but does our universe actually have computable PDFs, or is there something else? Will it really hold in this universe? Because, you know, in mathematics, we can imagine all these fantastical universes. And we can even, of course, imagine mythology. But that's not our subject. Our subject is the physical world, this universe. So there are some very strong physical arguments that show that our universe is a computable probability density function for any possible stochastic source. The first is the von Neumann entropy. Well, as you know, there are a few different formulations of quantum mechanics, but it all boils down to either a matrix or a vector as a wave function. You can just any wave function you can represent with a complex vector or a finite matrix. So that actually means that, well, we can calculate the entropy of any quantum system, any finite quantum mechanical system, and you can use von Neumann entropy for that. You can just search it and find it. It's easy. It's a trace of a matrix, and what that tells us is that the entropy, and that's von Neumann entropy is actually equivalent to classical entropy, and by another theorem, classical entropy is equivalent to algorithmic entropy, right? So that's why we know that the algorithmic entropy, algorithmic complexity of the stochastic source, if it's a quantum mechanical system, it should be finite. So that's the first thing. What is the second thing? Okay. Have you heard of this crazy guy called Seth Lloyd? Has anyone heard him? Okay, well, you should find out more about him. He's awesome. So he's a great inspiration for me, actually, because you know he started from he's a mechanical engineer at MIT, and he went on to quantum physics and actually he studied at the Perimeter Institute, which is this place for crazy physicists, not the normal physicists, but the crazy ones who really want to leap ahead and do something fantastical, right? And this guy went from mechanical engineering to quantum mechanics, and he calls himself a quantum mechanic. And, well, he has this paper called ultimate physical limits of computation, so 5 minutes. All right, that's cool. and in that paper, he shows that and in other papers, well, you can basically simulate any local quantum system with a computation, with universal quantum computation. And universal quantum computer is equivalent to universal computer. And so that's another argument for it. The third is the Bekenstein bound. And Bekenstein bound was conceived to make sense of black holes. What it really says is if you have a finite region of space-time and a finite energy, the total entropy in the system is bounded by a constant. So that actually works for any system and also for black holes. And it's the idea you can remember about the entropy of the black hole being defined by its surface, the 2D surface, and not the volume, right? Okay, so that's the third argument for it. That's also finite. And the fourth is that in cosmology, we can estimate the entropy of the observable universe. And that's the holographic bound for it, well, the bound that comes from information digital physics, OOF's bound, is 10 to the power of 123. So that's, well, big number, and most of it is dominated by supermassive black holes, but it's finite. So that means there can be no wacky things like hypercomputers or oracle machines or magical things like that. They don't exist in this observable universe, and nothing outside the observable universe would have time to travel here because of the speed of light limit, right? So that's the strong argument that Solomonoff induction is actually physically complete. And the second thing, I don't have much time for it. I get it, but maybe he'll give me a 2 minutes extension. He might, because he's enjoying the talk, right? Okay, so, and the second thing is, objectivity of induction. So we figured out completeness and objectivity. And there are some new measures. Well, so this definition of using the physical universe as the reference machine, what does that mean? Let's set the reference machine to the universe. This means we're actually eliminating the reference machine. So we're just assuming it can be any physical device, any physical machine. And then we have to quantify its physical resources. So what are the physical resources? Time, space, energy, basically. So you can quantify these. And there's a very straightforward way to, of course, translate the idea of algorithmic complexity, the shortest program that computes a bit string x, right, to this setting, which is the volume of the smallest machine that computes x. And that's just the volume of the initial machine, because the machine might grow in size, it might use more memory. But I found out that this definition actually improves some of the stuff in information theory. For instance, it's probably going to. There is a follow-up paper which is called Ultimate Intelligence Part 2. You can find an archive where we go into more theory. Okay, well, so we can use this definition instead of usual algorithmic complexity, but we can also go further ahead, and we can demand that this machine is self-contained in terms of energy. And this means that it has its own battery. So the natural step is, since all work in the universe requires energy, we can use energy instead of program size. We can ask for the machine, self-contained machine, that requires the least amount of energy. And then we can also go further ahead. And, well, as Carl Sagan said, if you wish to make an apple pie, you need to invent the universe from scratch, right? So what does that mean? It means, well, to construct anything, there is a cost. So you can also account for that cost, and I call that the constructive complexity. So how much energy does it take to construct this machine from scratch, and then run it, and then produce output X? So that's like the ultimate generalization of Kolmogorov complexity. And there is another definition that's also very nice, and it's probably the definition in terms of quantum computer, which is using quantum of action instead of energy. So how much cumulative quantum of action does it take to produce that machine and run the computation and simulate the PDF of stochastic source mu perfectly? And it turns out that this is a very nice definition, because in information theory you have these additive constants, right? So we're probably going to get rid of some of them if we pursue this line of thought, because you have these two machines, and you don't need any glue code. The universe is the glue code. They can just sit together and communicate via photons. So, well, thanks for listening, and if you have any questions, I'll be happy to answer them.